Hello, my name is Tobias Sundqvist and I'm an industrial PhD at Umeå University in Sweden. Previously, I've been working in the telecom industry for 20 years and developing the radio access network. Right now I'm doing research in how we can improve the radio access network, and today we're going to listen to a presentation about how we can use ensembles of Lon Short Term Memory models to find anomalies in the radio access network. The radio access network is an important part of the telecom system. It consists mainly of base stations and antennas, and its task is to make sure that the user equipment can communicate with the core network. The user equipment can be a mobile phone, a laptop, or some other equipment that uses the mobile network. As RAN has evolved from being something that only could handle calls, it has become a very large complex system that is used by billions of people, and it's also integrated in equipment everywhere. As the system becomes larger and more complex, vendors need to spend more and more time on testing and troubleshooting the system. In order to tell if RAN behaves normal or not, there are several metrics that can be collected and used both in testing and troubleshooting. You can collect performance measurements to describe the performance of applications, look at hardware and software configuration, which could tell which version and feature that's enabled. You can also look at the system logs from the different applications to see the behavior of the application. One thing that makes it really difficult to tell if the system behaves normal or not is the large amount of traffic that is handled by each base station. Troubleshooting such a system can be very tedious, since there can be hundreds of concurrent events every second. And as a troubleshooter, you need to be an expert of the system, and most time is spent in analyzing system logs in order to find anomalies and the root cause of them. Main research in the anomaly detection area uses performance metrics to detect anomalies. They can use CPU, memory, disk I/O, throughput, application-specific counters. But in RAN, performance metrics are often used to fine-tune the performance and find errors in the final stage of the development cycle. This is a little bit contradictory of what the vendors want. In order to save money and speed up the time to market, vendors want to find errors early in the development cycle. Since system logs are used from the beginning of the RAN development cycle, a new way to detect anomalies in these logs would be very beneficial for the vendors. When we talk about anomalies in this research, we mean application behavior that is not working as normal. Imagine you have a software that can manage different tasks. As long as the tasks are fulfilled, then everything seems normal. An easy anomaly to detect in this scenario would be that one of the tasks fails. More difficult anomalies could be that software consumes more money, uses more CPU, or takes a little bit longer time to fulfill the tasks than normal. As we analyze the system logs, we look at important printouts, which describe what the application is doing, and we call these events. If some events are missing in the wrong order, there are some extra events, etc., we consider this as an anomaly from the normal behavior. An example would be the events you see in the Apple use software in front of you. It has an abnormal behavior in all new versions of the software, and even though it could be a good use in some versions, the application is not behaving as it was meant to be. Instead of using experts on RAN to manually analyze logs, we want a model to learn the normal behavior from them. Since the RAN software is updated very often, it would be very beneficial if the model automatically could learn the new behavior without having to manually update the model every time the software changes. Machine learning models has been able to learn behavior from large data in many different areas, and if we could turn the system logs into a more suitable format, it would be possible to train a machine learning model with a normal behavior and then use it to detect the anomalies. Unfortunately, RAN system logs can contain data that is sensitive for users and vendors. Instead of using logs from the commercial live system, we used a 5G testbed created by TTEvery. The testbed can simulate a one-day scenario for a small city with 10,000 inhabitants. The advantage in using a testbed is that we can control the scenarios, repeat them, and also choose what to include in the logs without disturbing any live system. We can also simulate many types of anomalies, which is useful when testing different kinds of anomaly detection models. To be able to use the system logs for training a machine learning model, we extract important events and turn them into a numerical format where each number corresponds to a unique event. We then divide the events into sequences that belong to the same user equipment, and this is important since there can be thousands of concurrent services ongoing and they're all mixed up in the log. There are a lot of machine learning models available when it comes to prediction of time series, but not all are suitable for prediction of events in system logs. Recent survey of anomaly detection in system areas shows that recurrent neural networks is very useful in time prediction areas. The RNN learns from input and remembers previous values in order to predict the next value. An improved variant of the RNN is the Lon Short Term Memory model, which improves the memory of the RNN to be able to remember more events from the past and make better predictions. In most research, LSTM input and output are numerical values. Anomalies is then detected as predicted values that deviates from the real values. In our research, we have used another approach where the LSTM model outputs a prediction for different states to occur. These predictions are then used to detect the anomalies. To make a prediction, we use previous events as input and let the model predict the output. Instead of letting the LSTM model predict the most likely value, as in numerical prediction, we let the output from the model be the same as the number of unique events. In this way, we get the probability for each event given a previous series of events. We then compare the probability for the real event with the most likely event. In order to catch small but many deviations, we also multiply all probabilities for whole sequence to get a probability for the whole sequence. And if it's very, very low, then it's considered as an anomaly, but high, it's a normal behavior. As we performed experiments on the LSTM model, the sequence threshold was together a number of events to look back very important hyperparameters for the model. As we decreased the sequence threshold, seen in the top figures, more normal sequences was classified as normal, but as the probability decreases, we also let more and more anomalies slip through. Using many previous events to look back and decide the sort of next output was also decreasing the accuracy of the model. Events that happened long before in the past does not seem to help the model to predict the correct event. It rather confuses the model to make worse predictions for the anomalies. Even though we got a quite good anomaly detection using the LSTM model, we were not satisfied. Since it's important for the troubleshooters to get a model that can train extra on the misclassified sequences, we tried to improve the accuracy of the model by training extra on normal sequences that was classified as anomaly. In this scenario, the accuracy did not increase anymore. The model could be trained to be better in predicting anomalies, but instead it got worse in predicting normal behavior. Since RAN sequences contain large variations due to the many concurrent threads, it seems that the model gets problems where the variance increases. But in large variance cases, it's often useful to use multiple models that can help each other classify the behavior. Instead of using one single model to predict output, ensembles use output from multiple models, and there are three main categories of ensembles: bagging, boosting, and stacking. One ensemble that is very popular right now is the AD-boost ensemble. It trains a model on whole training data and then uses the prediction to let the next model train extra on the misclassified data. This is then repeated for all models used in the ensemble. As we perform some initial tests among the different ensembles, AD-boost performed best, and we continue our research using an ensemble of the LSTM, which we later will call BoostLog. Our experiments showed that the ensemble of LSTM models could deal with large variance in behavior. Already after 7 to 8 models, we got quite good result, and after 10 models we couldn't see any increase in the accuracy, neither in recall nor precision. Promising was also that the human-in-the-loop scenario, when training extra on misclassified sequences, increased the precision while keeping the recall rate high, meaning that the model still found many anomalies. To be able to compare our results with other research and also see if the models could be used in other areas, we tested our model on a Hadoop distributed file system. This dataset has been used by others to test their anomaly detection methods, and the results for the HDF dataset was very promising. We got an F-score of 0.97, which can be compared with previous best results that achieved 0.96. And previous results also used multiple features from the HDEF dataset, so it was interesting to see that our model could achieve such good results using only one feature. What we also can see in the table is that the ensemble model is much more beneficial to use on the round dataset. In order to understand why, we compared the normal behavior with anomalies for both datasets and found that anomalies differ much more from the normal behavior in the HDEF dataset. This might explain why it's more difficult for a single LSTM model to detect anomalies in the round dataset compared with the HDEF dataset. We can also see that a single LSTM model cannot handle increased variance in round data and won't improve when training extra on misclassified sequences. The conclusion from this research is that LSTM can be used in ADABoost Ensemble to improve the accuracy for anomaly detection. BoostLog is also very good in detecting many kinds of anomalies and found almost all of them. The most difficult ones to detect was single missing events. BoostLog also works great for other areas as well. On the Hadoop distributed file system dataset, it got better results than previous methods. What we also found is that it's important for the LSTM model to train on balanced data. In both the RAN and HDEF dataset, there were thousands of similar sequences. In order for our model to achieve good prediction, we only train on unique sequences. If we would have trained on all sequences, the model would have classified sequences that happens very seldom as an anomaly. In our future work, we will go further with anomaly detection in system logs and combine it with performance metrics. In this way, we can detect more anomalies and also find other types of anomalies. We'll also look into how the timestamps in the system logs can be used to detect anomaly behavior in the delays between the events. Later on, we'll also look at how we can find the root cause of the anomalies we have seen. Thanks everyone for listening. I hope you found it interesting. If you want to read more about this research, you can look up the boosted ensemble learning for anomaly detection in 5G RAN. And you can also read about my research at quistit.com. See you. Bye-bye.